start. So our next speaker is Suguman Bansal, who is a researcher at the University of Pennsylvania. And she will tell us about synthesis of coordination programs. And with that, thank you, Suguman, for joining us today. If there is supposed to be audio coming, I'm not hearing any.
Can you hear me now?
Yes, no, it's great. Thank you.
And do you see the slides in full screen? Let's do a quick mic check.
Yes.
All right.
Good.
Okay, cool. So thank you very much. Thank you, Russ. And thank you, organizers, for inviting me to the workshop. It's truly an honor to be here at Simons. So today I'm going to present coordination as another application to reactive synthesis, and I'll discuss its current and its future. This is based on joint work with Kedar Namjoshi and Yaniv Sar, and this paper appeared at POPL last year. So taking a leaf from Nir's talk today, that we're really looking at these settings where there are multiple agents, and we want to design a program that coordinates between them. And that's what we'll call a coordination program. And there are plenty of examples of these kinds of programs that we see in our regular daily life. For instance, a centralized coordinator in an IoT setup would be a coordination program. Here on this diagram in particular, I've shown a thermostat, and its task is to coordinate between a room temperature sensor, a heater, and an AC to ensure that the room temperature stays ambient. And other examples could include an automated industrial warehouse where a centralized coordinator coordinates between these several robots to ensure effective collaboration. Or at a much larger scale, the web services, where you have a centralized server that coordinates between several independently operating servers. All of these are examples of coordination programs. And what is of interest to us is that if you think of it abstractly, a coordination program is nothing but a reactive system. And here in this abstract diagram, the coordination program is in blue, and the environment is given by the set of all agents or devices between which the coordination program attempts to coordinate. And this is reactive because the devices and the environment in this case, which are the devices, the environment and the coordination program coordinate through a sequence of inputs and outputs, which is exactly what a reactive system does. Turns out, just like for every reactive system, specifying the intent of the program is simpler. For instance, in the thermostat example, the intent is simply that the thermostat should maintain ambient temperature. So to me, this sounds like the perfect recipe for a synthesis problem. So we'll define coordination synthesis, and the task is to automatically generate a coordination program from a high-level specification. Now, if the description of coordination, now this looks very similar to what we see in typical reactive synthesis formulations, say something like synthesis from LTL specifications. And if that were the case, we could have simply packed our bags and said that the problem is solved. Fortunately, that's not the case. There are certain characteristics to this coordination setup which make it more unique and make it more unique, which make it more unique and more interesting from the perspective of designing the synthesis algorithm. So one of the first characteristics is that the environment in this case, it's much more sophisticated. Typically in reactive synthesis settings, the environment is simply an adversarial system that generates inputs for the coordination program. But in this case, the environment consists of several complex looking agents or devices. For example, these agents could be things like room temperature sensors, ACs, heaters, and so on. So they are complex, they have complex, rich structures, and possibly even the ability to communicate among themselves. So they have some sort of an interface and all of that. So one could say that, well, all of this could be encoded in some form of LTL. And then But the argument would be that encoding such rich structure and such communication protocols in LTL would defeat the purpose of synthesis, which is that the specification is easy to specify. Next, from the perspective of what the function of the coordination program is, in this setup, the coordination program should be able to function under asynchrony. And this is because the environment, the devices inside the environment, each operates independently. So it would be incorrect to assume that there is a global clock along which all of the devices are synchronized. Instead, each device operates at its own clock. So there is asynchrony. So whatever coordination program we try to synthesize, it should operate under asynchrony. And finally, the coordination program only has partial information about the state space of all of the devices. This is because, think of it as an API. The API only exposes the signature, but we never really need to know what happens inside. So similarly, these devices, they may possibly interact privately among themselves without really exposing all of its functionalities to the coordination program. So despite this partial information, the coordination program needs to operate correctly. So these are the features, the characteristics that make coordination synthesis harder or harder than regular reactive synthesis. And that's really what we are trying to solve here. So the problem is to formulate, solve, and demonstrate coordination synthesis. And the idea in formalizing the problem is to ensure that the problem is easy to specify. And then from the perspective of algorithm design, to the best of our knowledge, prior work has not looked at combining all of the characteristics of reactivity, asynchrony, partial information, and to do all of this with rich LTL specifications. And finally, through some case studies, we'll demonstrate the utility of having a coordination synthesis tool. So now, diving a little deep, what is the high-level specification here? Well, to specify the intent of the coordination program, we will use LTL. What is important is that we will also specify the device descriptions as part of the input. And for this, we will use the well-established notion of communicating sequential processes, CSPs. And the benefit of using these, CSPs, is that in this language, we can easily specify these devices in a way where these properties of rich structure, communication models, and interface between what actions are visible to the environment and what aren't are available for free. So I'm assuming this audience is well aware of what LTL is. So I'll quickly give you a brief description of what CSPs are. So in CSP, each device is represented as a collection of CSP processes. And you can visualize it as this as a finite state machine where each state is called a process, and there are transitions between these processes on actions. In this talk, processes will be indicated by capital letters, and the actions will be partitioned into public actions, which are the actions visible to all other devices, and private actions, which are the actions visible only to that device. And transitions between any two processes are called evolutions. So on action A, so the process E evolves to process E0 on the public action A0, and similarly E0 evolves to itself on the private action B0. And of course, this language also allows for structural non-determinism. So from each state, it is possible, from each process, it is possible to evolve to two or more different processes on the same action. And here is a small example of what a device could look like in CSP. We could very well think of them as finite state machines. Now, when I say two or more devices interact with one another, intuitively, we could think of these as products of these finite state machines, where the rules of products where the rules of how to construct the product are given by the rules of CSP given by the rules of how CSPs interact or synchronize. And for this, the rules are different for public actions and private actions. On public actions, the idea is that two processes can evolve together if they share a public action. For instance, here, there are two processes, P0, P1, both of which share a public action A. So then collectively, collectively P0, P1 can evolve to Q0, Q1. However, if in this other example, P0 and P1 do not share a common action, a common public action, so no evolution occurs in the product. About private actions, each process can evolve on a private action by itself. There does not have to by itself without any dependence on other processes in the system. So here, process P0 has a private action, and it evolves to Q0 without ever interacting with the process P1. Here is an example just to give you an idea of what happens when two devices may interact. Here I have a device that initiates at process E and a device that initiates at process M. And when both of these interact, despite both of these processes being deterministic, the presence of private actions is enough for there to be multiple executions from the coordination of these two devices. And the fact that there could be non-determinism in the environment, in this case E, just magnifies the possibility of all executions. So, given this formalism, the coordination synthesis problem is defined as follows. Given an environment, given a set of n devices, given in the form of CSPs, E1 to En, and an LTL specification S, can we generate a coordinator M also in CSP such that when the environment E and the synthesized coordinator M compose, then all possible executions satisfy the specification S. Now, this is clearly a problem of reactive synthesis where E is the environment, M is the reactive system to generate, and S is the specification. But there are challenges in designing an algorithm for this, and those come from the inherent complexities of the problem domain. The first being, of course, partial information. In synthesizing, in the algorithm design, the coordinator may not be aware of the current state of E, and this is because of the environment, and this could be possibly due to two reasons. One is the fact that there is inherent non-determinism in the environment, and then the fact that the environment could take private actions without the information without ever having to inform the environment, as a result of which the environment may not know, as a result of which the coordinator will not know the actual state space. In addition to partial information, given partial information, it also becomes harder to ensure deadlock freedom. For instance, in this case, if the environment is given as such, then a coordinator that takes the action A0 would result in a deadlock. And this is because together E and M would evolve to the state E0, from which the coordinator M would not be able to coordinate with the environment anymore. However, however, a coordinator that takes the action A1 will not deadlock in the system. And the algorithm must have the ability to design a coordinator that does not deadlock, despite not knowing the actual state space of the environment. And if this was not enough, then there's also asynchrony. From the coordinator's perspective, it only sees the public actions. It never sees the private actions. So it doesn't know how many private actions have taken place or what the private actions are. So what it has to ensure is that although the coordinator only sees the sequence of public actions, for every possible expansion of that sequence that is valid in the environment, and by expansion, I mean all possible ways in which private actions could be interspersed in the sequence, the specification should be true on each one of those. And now our core result is that all of these challenges could be resolved using automata theoretic reductions. And what we show is that the coordination synthesis problem, given an environment E and a specification S, can be transformed into can be reduced into the problem of regular reactive synthesis from a transformed specification that we'll call TS here. So because we had heard a talk on, so in order to construct so now the question is, how is this transform specification generated? And this happens over a sequence of transformations from the automaton for the specification S and on the environment E. But there is one drawback with the flowchart I've shown you here. And the reason is that the size of, so if you think of the pipeline that we've generated here, in order to solve coordination synthesis from E and S, we can generate this transform specification. We can construct its automaton and then pass that as the input to any state-of-the-art reactive synthesis tool, and then we can solve, and then we could generate a coordinator M if it exists. But the issue with this pipeline is that the size of the automaton for the transform specification is exponential in the size of the environment and the number of states in the automaton for S. And this by no means would be existing synthesis algorithms will not be able to scale up, will not be able to synthesize for such a large automaton. So what we do is actually the following. We observe that constructing the automaton for the negation of the transform specification can be done very efficiently. I'll not go into the details of how this happens, but to construct the automaton for the negation, we only incur a blowup that doubles the number of states in E and the automaton for the specification. Now, if you remember the key idea from the talk on from the tutorial on bounded synthesis, is that if in a bounded synthesis tool, you want to synthesize for a given specification, then it internally constructs the automaton for the negation of the specification. And that's exactly the insight we can use here. Because the construction of the negation of the desired automaton, construction of the automaton of the negation of the specification is efficient, we actually use a bounded synthesis based tool in the backend to solve to solve coordination synthesis. So just to look at what the complete procedure is, at the front end, the inputs are an LTL specification S and a set of environments E1 to En, each EI denoting one device in the coordination setup. And then these inputs are processed by their respective state-of-the-art tools. Once the processing is complete, the inputs are sent into this co-reduction part. We perform the reduction through symbolic operations. And what this means in terms of the number of variables introduced is that because the state space is only doubled, this co-reduction only introduces one extra state variable to construct the automaton for the negation of the desired specification. And then this can be passed into a backend state-of-the-art bounded synthesis tool, and that will return realizable if it will return a desired coordinator if the input instance is realizable, and will return unrealizable otherwise. I do want to make another point here. So typically, So the tool we use here is BOSI. It is the state-of-the-art tool for bounded synthesis. And typically, internally, BOSI will convert the synthesis problem into either solving a QBF problem or a SAT problem. And the encoding here is done for general purpose specifications. What we observe is that if we incorporate some domain knowledge in creating these encodings, then the performance of the coordination synthesis procedure is improved by many-fold. And now to give you an example of how coordination synthesis can help. So here I've shown you how the I'm going back to the thermostat example. So the idea is that we want to synthesize a thermostat that coordinates between a room temperature sensor, a heater, and an AC process. Some of these actions are public actions and enable in coordination and so on. We don't need to get into the details of all of that. But to synthesize this thermostat, we could start off by saying in LTL to maintain ambient temperature. And then when we pass this through, when we pass it through our synthesis tool, it'll tell us, well, the problem is realizable, but the thermostat it synthesized was one that just did not interact with any of the devices. So what was happening internally is that the thermostat figured out that even if it never interacts with any of the systems, then infinitely often ambient temperature will be attained because of the changes in the temperature of the physical environment. But now this is obviously not, although this is correct with respect to the specification, it's by no means the intention of the specifier. So over a sequence of iterations, we could keep refining the specification to get rid of these undesired behaviors until we are satisfied with the kind of coordinator, in this case a thermostat, until we are satisfied with the thermostat. And this is really how we envision using a coordination synthesis kind of tool. And the basic idea is that we have been able to lift the debugging step from low-level debugging on the system to debugging at a higher level on the specification.
Suguman, just a note, here is your friendly timekeeper that we are 22 minutes.
And I am on my last slide, which coincidentally is also the 22nd slide. So this talk was about coordination synthesis. And what I did was I formulated the problem where devices are defined, where the devices are given as CSP environments and the specification as LTL. And from the algorithm's perspective, it's interesting because to do coordination synthesis, we have to we can combine asynchrony, partial information, and the full expressiveness of LTL. What I did not cover in this talk, but is an important point, is that the algorithm, that coordination synthesis is p-space hard in the size of the environment. And the algorithm I presented is exponential, although the reduction is linear and efficient, the full synthesis algorithm is exponential in the environment and exponential in the number of devices. And this clearly is a scalability bottleneck. If we wanted to make synthesis or coordination synthesis to become somewhat more useful for real life applications. And this, I feel, there is still a lot of opportunity to improve coordination synthesis and perhaps reactive synthesis in general. For instance, in our case, we saw that improving by doing domain specific encodings, performance can be improved many-fold. So probably the lesson to learn here is that if we are using synthesis tools as a backend, it may be more effective to open up the hood and try to search for opportunities for improvements. And similarly, one could make several, there are several opportunities for innovations at the algorithm level for reactive synthesis, and those would be interesting directions to explore in the future. I would conclude my talk with that. Thank you all for tuning in from your respective time zones.
Thank you. Other questions for the chat or the Q&A?
While we're doing that, we can transition to the next talk. So Suguman, if you can stop sharing.
Yeah.
Thank you. And so our final talk of the session is by Julie Newcomb.